Dear students, today let we discuss about the very important topic. It's from the structure of the atoms in your class 11 standard, right? So I just pick up the one of the important topic from the structure of the atom, that is the calculation of the energy of an electron in an orbit. Here, so here the orbits. I draw the structure of the atom. This is the structure of the atom. So in our atoms, okay, at the center of the atoms, here is the nucleus, okay. Around the nucleus, we have the number of the circular part where the electrons are revolving. So different number of the circular parts, different number of the orbits we drawn here, right? So that different orbits associate with different quantity of energy. That is what we call the cell or energy level. Cell or energy level, right? Okay, so this is the first energy level, this is the second energy level. This energy level which I drawn here, I just write here. Okay, this is the first energy level, second energy level, third energy level, fourth energy level, so on, right? So in our atomic structure, I mean in our atoms, number of the energy levels are there where the electrons are revolving. Okay, but the question is, so how much quantity of energy, okay, associated with the electrons, okay, in the first orbit, I mean in the first energy level, in the second energy level, in the third energy level. Since the different energy levels, okay, different quantity of energy associated with the electron. That means E1 is not the same with the E2, E3, E4. So all the energies associated with the electrons are different. So how to calculate these energy levels here? So we start to explain from the hydrogen atoms. Here, hydrogen atoms. How many electrons present in the hydrogen atom? Only one electron. Okay. What is the atomic number of the hydrogen? That is the 1. Okay. So this is the number of the protons and the number of the electrons here. So the number of electrons present in hydrogen atoms here. For the hydrogen atoms, okay. So we are going to calculate how much energy associated with the first orbit and second orbit. We have the formula. What is the basic formula? So we can remember here. This is the n energy level, right? N is the number of the orbits, so we can use the 1, 2, 3, 4, 5, 6, right? So this is the n energy level. So how much energy associated with an electron in the n energy level? So we have the formula, that is minus 2.18 into 10 to the power minus 18 into, so I write that Z is the atomic number square divided by n is the number of the orbit, which we write here square. So this value we calculate in the joule per atom. When we are going to calculate in the joule, I mean in the joule per atom, so we use these values. And on other hand, when we calculate in the kilojoule, so we found another quantity, that is okay. So we have 1, 3, 1, 2. So into Z square will remain here, and n square, that is the number of the orbit, multiplied by that is okay. What is the unit? Kilojoule per mole. This is the formula, right? So we can use this formula. We can use this formula. Then by using this formula, we can calculate the E1. Say for example, that we do. Now for hydrogen atoms, right? For hydrogen atom, I just going to calculate the hydrogen atom. Now here, what is the atomic number? That is the 1. So let me start from the n is equal to 1. So how much energy associated with the n is equal to 1 here? So let me put this one. Let me use minus 2.18 into 10 to the power minus 18. So Z here is 1 square. And what is the n here? That is also 1 square. What is the value? Joule per atom. What is the value here? Minus 2.18 into 10 to the power minus 18 joule per atom. So this is the energy. This much energy of the electrons, okay, associated at the first orbit. That means in the first energy level. So when we do calculate in the n, so E is equal to 2, that means n is equal to 2. This is second we calculate here, see, minus 2.18 into 10 to the power minus 18. Okay, here that will be remain same. Then so the number n is now comes out here 2 squared. So the values here, how much will come out here, minus, so that is the 2.18 into 10 to the power minus 18 divided by 2 square is the 4 joule per atom, right? So when we divided this, I think, okay, it comes out at 0.4554, so approximately 0.54 into 10 to the power minus 18 joule per atom, right? So this is the energy, okay? That means, okay, the first orbit is the minus is the charge of the electron, okay, and this is the charge of the electron, how much the energy, okay, that is the, we write here 0.54. So that means, okay, the energy, okay, here is the minus 18, here also minus 18, same. So this is the second, okay, energy of an electron in the second orbit, right? Okay, don't forget how do we calculate. So I think you can try the, okay, E is equal to 3, you can try E is equal to 4, and E is equal to 5, you can try, okay, you just do the calculate how much energy associated, okay, of an electron in the third orbit, in the fourth orbit, and fifth orbit, okay, so on. Then now when we do calculate at the highest energy level, suppose when we calculate at infinity, when we have the infinity, that means most highest energy level, that is called, we say the infinity. When we calculate this value, that means there is no energy state here, right? So that energy should be equal to the 0. So don't forget, this is the E infinity. So this is the E infinity. So how much energy? That is a 0. Don't forget, right? So when we calculate the 3, when we calculate the 4, when we calculate the 5, that means energy comes down and down, right? At the final, the energy will be the 0, right? So that you please remember, okay? Then when we do calculate the hydrogen, so we use the formula, but so the species, we have the other species, right? Species, we can say the ion, right? So ions, okay, containing the one electron, that means, okay, species or ion containing only one electron, that species we call the hydrogen-like species. Because we are explained here only the species, only the atoms containing one electron. Okay, here what are the hydrogen-like species? For example, helium, right? Helium, what is the atomic number of helium? Here is 2. Understand? Now, so how many electrons here? The number of electrons here is the 2. So now in order to change into the one electron system, that means only one electron. So one electron I remove from the helium atom. This helium atom is now from the helium plus. But the atomic number is same here. Atomic number is same, but the number of electrons here is only 1. So this helium plus we call the hydrogen-like species. Now here when we calculate the energy of an electron in the n orbit for the helium ion, that means for helium ion, right? What is the atomic number here? That is the 2. Okay, for the same energy levels, okay, as the hydrogen we calculate, right? So for the hydrogen, okay, just I write 4 hydrogen atoms, right? So E1 we calculate, that was how much we found it? E1. So that was, we write a minus 2.18 into 10 to the power minus 18 joule per atom. If we calculate in the joule per atom, so we have found this much. But if we calculate in the kilojoule, I think we can find like this. Okay, kilojoule per mole, right? This much value. This is the E1 for the hydrogen atom. But only the difference is here. See, what is the formula? I just remind you. That is the formula. This is the general formula. So if I write this, okay, minus 2.18 into 10 to the power minus 18. Here we multiply by the z square divided by n square, right? in the same energy level, but different species. For hydrogen, so that was the Z is equal to 1 square. But here, so for the helium that is a 2. So when we are going to calculate the first E1, so the first E1, that is the hydrogen here, how much hydrogen, that is minus 2.18 into 10 to the power minus 18. So we multiply by the Z square, right? That means, so when the Z increase, this E1 also will increase, right? So that means we found here how much for helium. So that is helium is the 4, that is 2 atomic number. Now what is that is minus 2.18 into 10 to the power minus 18 multiplied by 4. The value will become over here, right? So that means when the atomic number increase, so that is atomic number increase, this energy at the same energy level, right, also it increases, right? Understand? Don't forget. Say for example, when we are going to calculate E1, right? So another species, I just tell you. So when we are going to calculate for the helium, right? Helium class. Then when we are going to calculate for the hydrogen, right? So this one will be the highest, this one will be the highest, because the atomic number here is the 2, atomic number here is the 1, right? Okay, so the answer we found here. So similarly, I just give you another hydrogen-like species, right? So that is, I started from the lithium. What is the atomic number of the lithium? That is the 3, right? So this number of the atomic number is the number of the proton and the number of the electron. Here the number of electron is 6 or 3. Here number of electron is 3. Understand? Now here, so from the lithium atoms, how can we convert it into the species containing 1 electron of the lithium? That is, I remove the 2 electron from the lithium atoms. Okay, if we remove the 2 electron from lithium, so lithium will carry the positive charge. How many positive charge? 2 number of the electrons we remove, that is the 2 plus. So atomic number is same, but the number of electron here is now become 1. So we are going to find out the energy of an electron in the n orbit for the lithium. So similarly here we can use. Now here, so when we are compared another one, I just write beryllium. Atomic number is the 4. Number of electron is here 4. So in order to find the 1 electron system from the beryllium atom, we remove the 3 electron. We remove 3 electron from the beryllium atoms. Now it's only 1 electron is present. So what will be the beryllium? So beryllium is become the positive charge. How many electrons we remove? 3 electron. It should be carried to 3 plus. So here, so these all are the containing 1 electron here. So when we are comparing the energy of electron in the same energy level here. See, as I write here, atomic number increase, the energy also will increase here. So when we compare, so don't forget, this is very important. You remember it. That is when we are write a 1, right? E1. What about E1? If I write the beryllium 4 plus or 3 plus, right? When we compare this one and E1, another one is, I started from the lithium. So lithium 2 plus, no? Right? Then when I write this E1 for the helium 2 plus, then when we calculate the E1 for the hydrogen, so can we write the order of this, right? So as we know, this is the atomic number is the 4, here is the atomic number is 3, here the atomic number is 2, this atomic number is 1. So if the atomic number increase, the energy also will increase. So this is the order we can find. Okay, don't forget to understand. Now then, the simple formula. So how we could find out our key energy of an electron in the number of the orbits in different spaces. That only we just remind you. I write En is equal to minus 2.18 into 10 to the power minus I. This is for the hydrogen itself, right? This is for the hydrogen itself. Now when we write the helium, when we calculate the lithium, when we calculate the beryllium ion, so it will be multiplied by the Z square. That's only at the same energy level. So when we calculate the E1, so for the lithium, we can multiply by 3 square. Then for the beryllium we can multiply by the 4 square. That means we can find out for the different species, right? For the hydrogen-like species. Very quick answer we can find out, right? Don't forget. The next is now here. Okay. See, we are discussing. We are just find out how to calculate the energy of an electron in the n orbit. That's the idea. We can clear it now. So here, this is the structure of the atoms. I draw them. Okay, simple line. I draw like this, right? See, this is the n is equal to 1, 2, 3, 4, 5, right? One of the electron from the lowest energy level. Let me say n is equal to 1. So these electrons, okay, jump to the higher energy level. It may be 5, okay, it may be 4, it may be 3, it may be 2, right? Okay. So this is the lowest energy level, this is the higher energy level, 2, 3, 4, 5, 6, right? So now here, from the electron from the lower energy level to the higher energy level, right? So from the lower energy level to the higher energy level, electron jump. That is I write it jumping of electron, okay? Jumping of electron from where? From the lower energy level, from the lower to higher energy level. Higher energy levels, right? Now I start from here. N is equal to 1. Where the electron jump here, n is equal to 2. Okay, then another one, n is equal to 1. Where the electron jump to, n is equal to 3. N is equal to 1. Where the electron jump, n is equal to 4. N is equal to 1 to the n is equal to 5, right? That means different energy level. Here how much energy we calculate, how much energy we found when we calculate. So that energies are different, right? So electron jumping from the one energy level to the higher energy level, right? These types of the mechanism what we call excitation of electron. So excitation of electron means jumping the electron from the lower energy level to the higher energy level. These types of the mechanism what we call the excitation of the electron. Here is the excitation from the n is equal to 1 to n is equal to 2, from n is equal to 1 to n is equal to 3, right? So these are the excitation of the electron. Now in the excitation of the electron, okay, from lower energy level to the higher energy level, so energy required, right? How much energy required? Okay, the energy required for the different excitation will be different, right? That energy required for the excitation of electron, right? Excitation of electron. So we can calculate. So that is I write a delta E. This is the delta E. How much delta E? So how much delta E? How much delta E? We can calculate, right? So this is what we call the energy required for the excitation of the n is equal to 1 to n is equal to 2, n is equal to 1 to n is equal to 3, n is equal to 4, like this, right? So how do we calculate this energy required for the excitation of the electron? So we have a formula, simple formula, that is delta E is equal to, if you know the energy associated with the higher energy level minus energy associated with the lower energy level. check. For example, for the excitation of the electron, n is equal to 1 to n is equal to 2, right? So how much energy required for this excitation? That is, what is the higher? 2. What is the lower? That is the 1, right? That means that E1. So we learn how to calculate the E1, how to calculate the E2, right? We have the formula. What is the formula? If I use to calculate in a joule, so we write 2.18 into 10 to the power minus 18. Okay, if I just calculate for the, okay, so for different spaces we have to multiply by the z square, then n. That is, what is the n? 1 square. If we calculate for, that will be the 2 square. So these things are same. Then the values found here, we can put here, the answer will be found here. That is the amount of energy required for the excitation from the n is equal to 1 to n is equal to 2. That is the simple calculation. So this energy here, okay, so we can practice to do here. See, I just tell you for the hydrogen, okay, for hydrogen atom, how much it was? E1, that was, I used that one, okay. In the other form, that is, we can use the E1 is equal to, also in the kilojoule we can write minus 1312, okay, into z square divided by n square. So n is the 1 square. So this is the kilojoule per mole, right? If we use the kilojoule, we can use this one. If we use the joule, we can use this value. Let us use the kilojoule, okay, in a very easy way, right? So E1, how much for the hydrogen? So that is z square is 1 square. That means 1 minus 1312 kilojoules. If we are going to calculate for the E2, how much for E2? That will be the, okay, when we calculate for E2, that will be the minus, okay, 1312 divided by 4. How much will be here? That will be the, I think, okay, again 4, 3, then 3 minus, then 5 and 6. This much kilojoule we have, right? So when you have this much, okay, when you have this value, so how we can calculate the ionization energy for this excitation? That is the minus 356, okay. No, this value which will be wrong. That how much? Marine trintoid, marine trintoid, marine con, then marine kun. This must value, I think, right? Then now, when we found this value, okay, you can calculate actually how much we can come from value. So when we have this value E2, then minus E1, so we can find this value here, right? So in that case, in that way we can calculate, right? That means, so excitation of the electron, that means the, okay, jumping of the electron from lower energy level to higher energy level. So that excitation of the electron, we can calculate how much energy we can calculate for the different excitation of the electrons. So the formula is as I show you now here, okay. Then here, so the excitation of the electron, okay, different, okay, same excitation of the electrons in the different spaces. So how can we compare it, right? See, for example, here. See now here, let me show you the excitation of the electron. N is equal to 1 to n is equal to infinity, right? So this is also excitation of the electron. This is the highest electron. So how we can calculate this delta E is equal to, what is the highest? E infinity minus E1, right? So this is for hydrogen atom. I start from the hydrogen atom, right? So what is the value of this? Already I given to you 0 minus, how much this value for hydrogen? So let me write a minus 1312 kilojoule, right? What is the value? Plus 1312 kilojoule. This much energy is required for the excitation of the electron from the lower energy level to the infinity, right? If we have this excitation, when we calculate for the helium plus same excitation, suppose n is equal to 1 to n is equal to infinity, right? So how can we calculate this ionization? That means energy required for such excitation, right? So how much? E infinity same, right? Then here also E1, okay? So same value. So when we calculate this one, so here, so this value is 0 minus E1. What is the E1? We know that is minus 2.10. Let me take this one. Let me take 1312 into z square divided by what is it? 1 square. Same 1 square, right? So here z square is more. This 1312 is same here. Okay, same 1312 is same here. Only the just addition is z square. So here I write it. That means this delta E. This is for the hydrogen atom. What the value is found here? So we multiply by the z square. That is for the our helium, right? Helium. This is for hydrogen atom, and we multiply by the atomic number of the helium. So that is for the delta E for the helium. So we can calculate delta E. What we found the hydrogen atoms. Then multiply by the z square. What is the z for this helium? That is the 2. So we just can calculate, right? Simple way. Then see how much we can find out here. See, for the same excitation, n is equal to 1 to the n is equal to infinity. So for the hydrogen atom, what is the energy required for such an excitation? That was 1312 kilojoule. So for the helium ion, for the helium ion, same excitation. How much this helium? That means delta E for the helium, right? So is equal to, this is delta E for the hydrogen atom multiplied by the z square. What is the z for the helium? That is the 2, right? That means how much for the hydrogen? 1312 multiplied by, that means 2 square, that is a 4, and the answer we find here, right? So this is the way how we can calculate very quickly, right? Now here, the ionization of our hydrogen atom. I write this ionization. Ionization of hydrogen atom. I mentioned here. So this is the hydrogen atom. Ionization means formation of the ion. Ionization means formation of the ion. How these hydrogen atoms form the ion? That is, I write hydrogen ion, right? So how this hydrogen ion form from the hydrogen atoms? We remove the electron. Here atomic number is 1. How many electrons here? That is 1, right? So 1 electron from the hydrogen atoms remove here. 1 electron. We remove it. This is what we call ionization of the hydrogen atom. In this ionization of the hydrogen atom, from where the electrons remove, this is our atom. This is the hydrogen atom. 1 electron is present here. This electron is removed, right? This electron is removed. Where electrons go? Electrons goes to the infinity, right? These electrons goes to the infinity. How much energy required to remove the electron from the n is equal to 1 to the infinity, right? Infinity means the electrons goes to somewhere else, right? So how much energy required? That we calculate here, This delta energy related to the ionization of the hydrogen atom. That means how is the ionization of the hydrogen atom? So in the hydrogen atom, the first electron is present in the first orbit. This is the first orbit. How much energy here? So we know how to calculate. So that electrons is goes to the somewhere at the infinity, right? What is the energy at the infinity? That was 0. Then how much energy required to remove the electron from the n is equal to 1 to the infinity? It's already calculated. But only the thing is that what these terms code I just mentioned here, that is ionization energy, sometimes we call, or sometimes we call ionization enthalpy, right? So sometimes we are asking to calculate the ionization energy for the ionization of hydrogen atom. It's same case we did the calculation. How did we calculate here? So it's the same case here. Delta E is equal to E infinity minus E1. How much it was? So sometimes it may be given here E, this E, and it's equal to minus 2.18 into 10 to the power minus 18. This is for the joule per atom at the ground state, means n is equal to 1. If this value is given here, so we can put here this value, and this value is already 0, and now minus, again minus, the answer is here. So this is the plus 2.18 into 10 to the power minus 18 joule per atom. So now this value we shall call ionization energy or ionization enthalpy for hydrogen atom. Don't forget it, right? Very important. Similar. So in the case of the helium, right? Helium plus, right? So now here, what is the atomic number of helium? That is the 2. So here in this, how many electrons are there? That is the 1 electron. Now what is the structure of this helium? It's this one. This is the helium atom. Let me say helium atom. Helium atom, how many electron? That is the 2 electrons. That means 2 number of the protons, 2 number of electrons. Now here the structure of the atom. In the first orbit, the maximum number of electrons can be accommodated here is 2. Then now one of the electrons is removed. I remove the one of the electron. This electron I remove here, right? So I just take out one electron. Now this helium, it becomes only one electron present. So this now is the helium plus ion. So now here electron, one electron. Now here from the helium ion, this electrons I remove. I remove. So this electrons goes to somewhere. Suppose it's infinity, right? This type of the removing the electron, this is also ionization, right? So this helium plus, now one electron is removed. One electron is removed. So already this helium carry the positive charge. Again one electron is removed. No electrons remain here. No electrons remain here. So this helium plus it become the already plus. One electrons more removed, that means 2 plus, right? So here, so from the first orbit n is equal to 1, how much energy that was calculated? Then this also we know E infinity is a remain 0, right? So now the energy required to remove the electron from the first orbit to the infinity, right? So how much energy required? This energy also what we call ionization energy, of the helium plus ion. How much ionization energy of this, right? Same calculation we can do here, right? That means for this, so we know that this is the 0, right? 0, and this is the value what we can find out here. Only the difference is this one. In this value, that means minus 2.18 into 10 to the power minus 18. Then here it should be multiplied by the z square, right? That means the ionization energy for the hydrogen, this is for hydrogen. this is the ionization energy for the hydrogen, this is the ionization energy for the helium ion, right? So this ionization energy for the helium ion and ionization energy for the hydrogen atom, it's not the same, only the different here, so it's multiplied by the Z squared. What is the Z here? That is the Z is the atomic number of the helium, okay, plus ion. What is the atomic number? So we know that is the 2, so we can multiply this value, right? That is the ionization energy for the helium plus, right? So these are the calculation, how can we do it. So in our competitive examination, the quickest method to find the ionization energy of different species, these are the some sort of the idea I just share with you, you try to understand, okay? So I think you can enjoy this lecture, okay? So I think you can learn some good idea about our calculation of the energy and ionization energy of our different species, right? So please try to understand it. Thank you.